Alright, so we get these two equations from our previous example with the train. We have the point of view from inside the train. Light travels this much distance with this given, the speed of light times that time. And the same instance, it appears, that light travels this much distance, c times t. And it's obvious that those t's cannot be the same. They cannot be the same value. In the bottom equation, it's traveling further. Imagine that this is thing traveling a heck of a lot faster, like near the speed of light. Then it's clear that the speed of the time in both equations cannot be equal to each other. So let's solve for that relationship. First thing I'm going to do is I'm going to take this and I'm going to plug it into there. Okay, so that gives me this equation. Well, and I'm using white to separate the point of views. Okay? Now, I don't like square roots, so the next thing I'm going to do is I'm going to eliminate that square root. And how I'm going to do that is I'm going to square everything. So if I square everything, I'm left with c squared t squared is equal to v squared t squared plus c squared t squared. Now, V's and C's are constant. They're usually something that's given to you in the problem. The variable in this case is time. Those two are two separate time values. So what I'm going to do is I'm going to separate those the time values. So I want to get all the like times on one side and all the other times on the other. Okay? So I'm left with ct squared minus v squared t squared is equal to c squared t squared. Okay? Cool? Now from here I'm going to go ahead and I'm going to pull out a c squared. I don't like seeing c squareds on both sides. I know they're the exact same number, so I want to simplify that. So what that's going to look like is it's going to look like this. I'm going to have c squared times t squared minus v squared over c squared t squared. Okay? If you're trying to figure out where that c squared came from, imagine here between the v squared and the t squared is a c squared over c squared. It's 1, so it really isn't going to contribute anything. But when I pull the c squared out of the top, I'm still left with the one on the bottom. Okay? Is equal to c squared t squared. Okay? Those cancel out. And the next thing I want to do is I want to pull out a t squared. So I'm going to have a t squared here is equal to, 1 minus v squared c squared is equal to t squared. Okay? We could be done at this point. I mean, we've pretty much got what we need. But we want to simplify it a few more steps. First thing I want to do is I want to move this over to this side. Okay? And then lastly, I'm going to take the square roots of both sides, and I'm left with t, from the point of view of the person outside of the train, is equal to the t from the point of view inside the train divided by the square root of 1 minus v squared c squared. Okay? That is the time dilation equation. This right here is the time dilation equation. Cool? Now, it's simplified. You'll probably see it expressed this way in most books. T is equal to T gamma. And gamma is nothing more than 1 over the square root of 1 minus v squared c squared. Okay? That gamma is a relativistic correction. You'll see it over and over again. So what they're doing is they're just going to say this relationship, this 1 divided by the square root of 1 minus v squared over c squared. Let's just call it gamma. And you're going to use, like I said, you're going to use it in energy. You're going to use it in length contraction. You're going to use it in momentum. This is reoccurring, okay? So that right there is the time dilation equation. Sorry, that one and that one. Cool? Next is the length contraction. I'm just going to give that to you. I am not going to derive it. And then we're going to talk about simultaneous events. All right?